So generally, if you look at like numerical analysis textbooks, they separate the sources of error into two different sources. So one of them is round-off error, and the other one is what's known as truncation error. So we're going to spend a lot of time talking about round-off error, and then we're going to mention truncation error briefly at the end. And then finally, at the very end of this section, we're going to talk about experimental error, which we're going to get to at the end of class in a little bit more detail. So let's start off with round-off error. So what is round-off error? Round-off error is basically when you don't have enough sig figs for your calculation. So let's take a look at an example here. Let's say that I have a variable a, and I'm going to say a equals to 1. Let's say I have another variable, and I say b equals to 1 plus 10 to the minus 5. And then let's say I have another variable, c, which I define as b minus a. So question, c equals what? And this is confusing because I use the variables a, b, and c, but this is going to be a poll. Okay, so the poll, a, c equals 10 to the minus 5. B, c equals 0. C equals something else. In parentheses, it depends. Okay, everyone's answered. And so if you look at the results here, you can tell that y'all were suspicious of me and you thought this was a trick question, right? Okay, some of you put the mathematically correct answer, which is 44%. This being a numerical analysis class, some people said, well, I don't know, maybe it's a trick question, maybe it's 44%, especially when we're talking about round-off error, right? This is a section on round-off error. So you're thinking that, right? Your spider sense is tingling. And then maybe some of you were hedging your bets and said, well, I don't know, it depends, right? And it's kind of all three are the right answer. It depends, right? It depends on how many sig figs you have. So if you look in MATLAB, or maybe I should say in a computer program, A might look something like this. 1.000000, and B might look like 1.00001, 0. Is that 10 to the minus 5? Right? And so then C would be equal to 0.0001. Wait, there's one more 0, right? Did I get that wrong? 0.1. Or 0 if you had 5 or fewer sig figs on B. And that's exactly the problem, is that it depends on how many sig figs you're carrying along and when you're doing your round off. Now it turns out that MATLAB can carry way more sig figs than just 5. And so MATLAB should be able to handle this. Let's go ahead and see what it looks like in MATLAB. So in MATLAB, you can say, well, A is equal to 1. B is equal to 1 plus 10 to the minus 5. And C is equal to B minus A. And you can see MATLAB was like, okay, that's 10 to the minus 5. Cool. All right, so MATLAB can handle it. Right? So in general, when you're doing your calculations, even if you don't normally carry this many sig figs, you need to wait until the very end of your calculations to do the rounding, right? I mean, that's what y'all do anyway, probably. But even that has limitations, because your calculator, or MATLAB, even MATLAB, has limitations on the number of sig figs it stores. Right? So MATLAB can't store an infinite number of significant figures, because then it takes up an infinite amount of area, and it will take an infinite amount of time to do calculations. So MATLAB stores a certain number of significant figures, and in general, when you do scientific computing, you have two different kinds of numbers. You have what are known as single precision numbers, and single precision numbers have like 7 sig figs. And you have what are known as double precision numbers, and double precision numbers have 15 sig figs. So that's why MATLAB can handle the computation we just did, because it carries out 15 significant figures. So 1 is really a 1 point and then 14 zeros afterwards. Or is it 15 zeros? I can't remember which. That's called a double precision number, and that's just normally what MATLAB does when it works with numbers. In fact, if I go back to MATLAB and I click on my workspace, it tells me, let me expand this out. Okay, it doesn't tell me on the scalars, right? So it doesn't tell me that A is a double and B is a double, but this capital A, this matrix, it says it's a 9x2, what? Double array. Because it's a double, right? And you can ask, what is A? And to do that, you type in the command who's A, and you hit enter, and it tells you it's a 1x1 double. So it's a double precision number, and it takes up 8 bytes, because that's how much a double precision number takes up. In fact, I've never even worked with single precision numbers in MATLAB before. Just by default, it does double precision. Okay, so since double precision carries 15 sig figs with it, if we do the exact same exercise here, but instead of 10 to the minus 5, what if we do 10 to the minus 15? Then we're pushing the limits of what MATLAB can handle. So I can do the same thing that I did before, where A is equal to 1, and B is equal to 1 plus, now I'm going to say 10 to the minus 15. Now if I do the poll and say, well, what is this going to be equal to? Are you going to say 0? Are you going to say 10 to the minus 15? What are we going to say? And the answer is, it tried. It tried. It got kind of close, right? But obviously there's error with it. What happens if I do 10 to the minus 16? Now what is it going to do? Now it's just 0. Like, you can't handle it. What about 10 to the minus 14? It still tried. It's getting closer to actually exactly 10 to the minus 15. But even 10 to the minus 14, it still has some round-off error associated with it. And so the point of all this exercise is to show you that if you're working with numbers where round-off error starts to be a problem, then you, then it's a problem. Yes? Oh yeah, that's a good question. So if MATLAB is storing 15 sig figs, why doesn't it get this correct exactly? And the answer is, I don't know. There's some magic that happens with, like, you know, it doesn't exactly store the right amount of memory or something like that. I'm not exactly sure. But the point is, when you start to push this limit of the 15 sig figs, even before you get to that limit exactly, you start to accumulate some error in your floating point arithmetic.